Good afternoon, good evening, and good morning to all our delegates attending from different parts of the world. Welcome to the fifth plenary session of 7th International Conference on Recent Advances in Geotechnical Earthquake Engineering and Soil Dynamics. In this session, there are two keynote presentations which will be delivered by Professor S.K. North and Professor Amir Kenya. And this session will be chaired by Professor J.T. Sahu, my teacher from IIT Delhi, and Dr. Arun Gupta, our good friend from Ministry of Earth Sciences. Before I hand over the session, I would like to briefly present the short bios of Professor J.T. Sahu and Dr. Arun Gupta. Dr. Sahu received his MTech and PhD degrees from IIT Kanpur, India in 1988 and 1994 respectively. He did his postdoctoral research at Institute of Lowland Technology, Japan from 1996 to 1999 and again visited Japan in 2006 to 2007 as visiting professor. Dr. Sahu joined IIT Delhi in 2002 as assistant professor. Presently, he is HAG professor at IIT Delhi. His main research interests are geotechnology for roads and railway tracks, ground improvement, and geosynthetic applications. He has more than 60 papers in reputed journals. He co-edited 6 books and has supervised 52 MTech and 10 PhD theses. He has completed 11 sponsored research projects and more than 100 consultancy projects till date. Dr. Sahu is an editorial member of Transportation Geotechnics Journal, Royal Society Open Science Journal, Indian Geotechnical Journal, and Lowland Technology International Journal. He was chairman of IGS Delhi chapter from 2015 to 2017, and he is a honorary secretary of the Indian Geotechnical Society since 2007. Our co-chair, Dr. Arun Gupta, is presently working as Scientist E in the Ministry of Earth Sciences, New Delhi. Prior to joining the ministry, Dr. Gupta worked at Wadia Institute of Himalayan Research, Himalayan Geology, Dehradun, and Institute of Seismological Research, Gandhinagar. He was actively involved in the setting up of Gujarat's seismic network and multi-parametric geophysical observatories in Kutch region. He worked on seismic wave attenuation characteristics and estimated first-time seismic wave attenuation factor using CODA waves for Saurashtra and mainland Gujarat. Dr. Gupta also taken up research related to earthquake intensity, seismicity analysis, seismic hazard assessment, and site characterization, and brought out very good publications in SCA journals. Since last 8 years, he is playing an important role in the ministry and contributed significantly in coordinating various programs under seismological and geosciences. With this brief introduction, I hand over the session to Professor J.T. Sahu and Dr. Arun Gupta. Please, sir, please take over. Professor Sahu, your mic is muted.
Thank you, Professor Ravi Jakka. And without further losing any time, I request my co-chair, Dr. Arun Gupta, to introduce the speaker, the first speaker, S.K. Nath, Professor S.K. Nath from IIT Kharagpur. We will have another speaker after the first presentation then. Okay, please go ahead.
Thank you, sir. So Professor Nath is a very well-known geophysicist and seismologist of India, and he doesn't need any introduction. So as a customary, I will read something, whatever is there. So Professor Nath was born in 1960, and he is a geophysicist, seismologist, and a senior professor at IIT Kharagpur. He is known for his geomorphological studies and an elected fellow of the Indian National Academy of Engineering, Indian Geophysical Union, National Academy of Sciences, India, and West Bengal Academy of Science and Technology. He has amply been successful in making an excellent blend of exploration and solid earth geophysics and earthquake hazard science and engineering with ranking contribution in near surface imaging, source, path, site, and ground response characterization, landslide and liquefaction susceptibility, zoning, seismic hazard, vulnerability, and risk microzonation, so vitally needed for our globe. His study has been documented in several peer-reviewed articles. Online repositories of scientific articles have listed 250 plus of them. He is the author of Seismic Microzonation Manual and Seismic Microzonation Handbook published by Ministry of Earth Sciences, and edited the training handbook for the faculty of state resource institutions, capacity building and earthquake risk management published by Ministry of Home Affairs. Professor Nath is also credited with the establishment of a strong motion network of 16 earthquake monitoring monitoring stations in Darjeeling, Sikkim, Himalaya, and one national broadband seismological observatory at IIT Kharagpur. He has also received National Mineral Award of Ministry of Mines in 1999, and CSIR awarded him Santi Sarup Bhatnagar Award, one of the highest Indian Science Award, in 2002. So with this brief introduction, I would request Professor Nath to present his keynote address on the title Regional Local Hybrid Seismic Hazard and Disaster Modeling of the 5 Tectonic Province Ensemble of West Central Himalaya to Northeast India. Thank you.
Thank you very much, Professor Dr. Gupta and Professor Shahu. With your kind words, I am just sharing my screen and putting it in the presentation. Sorry for the technical glitch. Professor Shahu, Dr. Gupta, Professor Ravi Jakka, esteemed colleagues and the participants, warm greetings to all of you from IIT Kharagpur and on my own behalf. I am going to make a presentation on the regional local hybrid seismic hazard and disaster modeling of the tectonic ensemble of the West Central Himalaya, Northeast India, and with specific emphasis on some of the key cities in this ensemble of 5 tectonic provinces. As we all know, earthquakes are the most threatening natural disaster to the mankind, killing thousands of people every year and damaging properties worth billions of dollars all over across the globe. The seismic loss doesn't depend only on the tectonic provinces, but also depends on the vulnerability component and the exposure and the implications of all the urban, semi-urban, and the rural settings of the structure and socio-economic aspects of it. This is the agenda of my presentation. First, I will take you through the seismic hazard and risk of the Indian peninsula as a whole. And then I will take you to the ensembles with a slightly higher order of disaster modeling. That includes site classification, site response analysis. And then I will also go into the secondary seismic hazard induced by the secondary phenomenon because of the primary earthquake triggering, like in the valleys, it is the liquefaction, and in the hills and the rugged topography, it is the landslide. Then I will look into the implications of these hazards on urban structures, and then I will come and conclude my presentations. So let me first go into my the first presentation. As we understand, the whole of India comprises of the 11 morphotectonic provinces. The Bengal Basin, which is sitting here, which is visited by 1885 Jamuna earthquake, and with having an ensemble of the Eocene Hinjol and the intersection with the Jamuna fault, and it has an MC of about 6.8 plus minus 0.4. Then we go into Indo-Gangetic four-deep region, which has been crisscrossed by several tectonic patterns like the Patna fault, the Ravati fault, and also it is in the very close proximity of the Himalayan, central Himalayan the segment, and which takes into account the entire 2,500-kilometer long Himalayan belt, which is the neotectonic and the active tectonic part of the Indian peninsula, which is under constant threat and is producing earthquakes of the order of more than 6 to at the as high as 8.3 that has been rocked by 1934 Bihar Nepal earthquake. So Indo-Gangetic Fort region has an MC of about 7.7 plus minus 0.4. Then we go into Central Indian Peninsula Shield that was visited by Jabalpur earthquake in 1997, which has an MC of 7.3 plus minus 4. Kutch region, which was visited by 2001 Bhuj earthquake of that has devastated the entire the Kutch region and the Gujarat. All the cities, whether the Bhuj, the Jamnagar, the Ahmedabad, all of them were rocked by this earthquake, and it has the MC of the order of 7.3 plus minus the 0.4. Koyana region, which was which was triggered 1967, the reservoir triggered Koyana earthquake, which has a magnitude 7.2 as the MC. With this Western Ghat mobile belt, it has an MC of 6.4, 6.0. The Eastern Ghat mobile belt has 6.4, and Kashmir earthquake, which was rocked by the Muzaffarabad earthquake in 2005, we call it Muzaffarabad Pakistan earthquake, and it has an MC of the order of the 8.6 plus minus 0.3. West Central Himalaya, which was visited by the Uttarkashi, the Chamoli, and also the most infamous the Kangra earthquake, and this has a MCO of the order of 7.8. Darjeeling Sikkim Himalaya, which is where I have been working for the last 25 years as of now, has an MC of 8.1. And Northeast India, which is divided into 4 ensembles of the Mishmi block, which has an MC of the order of the Mishmi block has an MC of 8.7, which was visited by 1950 Assam earthquake. The Shillong seismic zone, which was visited by 1897, the Shillong earthquake of 8.1. And Eastern boundary zone has an MC of 8.2, and Shillong zone has an MC of 8.7, and Eastern boundary zone, which has an MC of the order of of 8.2. So with this situation, we have divided the entire India into 11 tectonic provinces, which is the seismogenic provinces that has been considered in this study. And if you look at this diagram, we have a hugely clustered network of the active neotectonic faults, and earthquake catalog, the declustered earthquake catalog of 1900 to 2018, which has been used here, which comprises of about 58,366 main shock events. So you need, for this kind of study, you need for the protocol, we need the database of seismotectonic model, logic tree framework, and an output. And this needs an earthquake. The seismotectonic model needs an earthquake catalog, tectonic faults and lineaments. The size has a conservative seismicity and the ground motion prediction equations with that. So in seismotectonic model, the first and foremost thing is the layered seismogenic sources. There are many school of thoughts which consider layered seismogenic source is the only source, and there is a second school of thought which uses the tectonic sources as the only source. And we have for the ensembles, which is my focus of attention of this presentation, has been considered both the layered polygonal seismogenic sources at 4 seismogenic the levels and hypocentral depth levels, and also the tectonic sources. In seismicity, we have used the declustered earthquake catalog I just discussed, which gives you a recurrence rate, maximum earthquake prognosis, polygonal and tectonic seismic activity rates, and also a host of ground motion prediction equations, including the next generation attention models, which we have developed as a part of the present study, and a logic tree framework where we have considered the layered polygonal sources as one with 40% weightage, 60% weightage is the tectonic sources. Then we have a the threshold magnitude of 3.5, 4.5, and 5.5 for this particular earthquake catalog. So each has a 3 basically complete magnitude out here, and then we go into seismicity model with plus minus 0.32 of delta max, and in all the 3, and then the sources which is defined here, and then the tectonic provinces, and the ground motion prediction equations which are being taken into consideration, and the final output is the PSH at the engineering bedrock. So we have divided the entire Indian peninsula into 172 polygonal seismogenic sources at 4 the hypocenter depth ranges 0.25, 25 to 70, 70 to 180 kilometer, and 180 to 300 kilometers, which are called deep-seated zones. The focal mechanism evolved, evaluated by summing up all the moment tensors which are being extracted from the centroid moment tensor analysis, have been embedded and has been put out here in all of them, and at the 4 different seismogenic depth levels. So with this, I go into giving you a glimpse of what exactly is the seismicity parameters which are being used by using a Gutenberg-Richter relationship, and then modified by using a Gutenberg-Richter tapered seismicity model, wherein lambda m is the cumulative number of events with magnitude greater than m, and b value is the slope parameter that has been used into computation, and as an exponential of this here. And I have shown some seismicity. I'm not elaborating all of them because the time will not be that much to elaborate each and every one, just by showing you the glimpse of some seismicity analysis and some of the seismogenic provinces. Zone 12, which has an A value of 3.45, B value of 0.72, and the M max observed is 7.6, and M max calculated is 8.6. And it is at zone number 21, A value, B value, maximum observed and maximum predicted is shown out here. Zone 72 plus 73 combined together gives a value, B value, and all of them are required for calculating the activity rate, as well as and then it is a maximum earthquake observed, and the maximum earthquake that has been predicted is 7.3. This is for zone 63, this is for zone 28 plus 30, and this is for zone 25. So this has been done for all the 172 polygonal seismogenic sources, and a bookkeeping has been done, and these are being stored in the cloud as a storage clusters. And then after this, next comes the activity rate for each and every polygonal seismogenic sources. So we went into smoothened seismicity models, wherein we have used this equations, which is lambda is equal to NR, MR divided by T, where MR is the number of earthquakes of magnitude M, the threshold magnitude M, MR and above. And NMR is the activity rate that has been calculated is by using this equation, and where this represents where NMR is the number of events with magnitude greater than MR, Dij is the distance between ith and jth cells, and C denotes the correlation distance. The annual activity rate is computed each time as NMR divided by T, where T is the sub-catalog period that has been taken for each of the seismogenic provinces. So here I show this also gives you a proxy about the aspherity, zone of aspherity at different depth levels. So this is hypocentral depth level as 25 kilometer and below. This is between 25 and 70. This is between 70 and 180. So if you see here, except in the Northeast Indian region, the seismic activity rate or the stress concentration is not that significant. The next very important thing that comes in is the definition of the bedrock. What we did is we used Allen and World's relationship, and by using the topographic gradient map of the India, and using this topographic gradient map of India, and by using the Allen and World's relationship, we have divided active tectonic and the stable continental region into the NEHRP site classes B, C, D, and E, where B is greater than 760 meter per second. C is between, it goes from 360 to 760. D varies between 180 to 360, and E is less than 180 meter per second. So BC, the boundary between BC is the engineering bedrock that has been considered. And if we see and plot the whole of it for the India, we can see that the most of the Indian peninsula is pertaining to the site class between B and C. So therefore, we have considered BC as the engineering bedrock to which the probabilistic seismic hazard of the whole of Indian peninsula pertains to. Then comes then comes the ground motion prediction equations. We have used two next generation attenuation models of Buru and Atkinson as the classical model, and the second one by Campbell and Bojognia. And using this for all the ensembles, we have developed about 120 ground motion prediction equations. These are spectral ground motion prediction equations for each and every time period. Apart from this, we have also taken the ground motion prediction equations which have been published by Sharma et al., Parvez et al., and others, and also the regional as well as the global the ground motion prediction equations have been taken depending upon what is the whether it is for the active or the passive belt. So with this, we select the ground motion prediction equations. Then we take a computational protocol for probabilistic seismic hazard of the Indian peninsula, which has been published by Cornell 1968 and Estawa 1956. And with this, and this is the equation which gives the probability of exceedance of a value small a above A with the activation rate lambda I, with P as the probability of A exceeding A where for a given magnitude M at the source to site distance R, and with FM and FR and F sigma, these are the probability density functions pertaining to magnitude, the distance, and the and also the ground motion prediction equations that we are using. So these have, all of them have some probability density distribution. Like we have the for magnitude, it is beta into exponential of minus beta into M minus M min by 1 minus exponential of beta M max minus beta is obtained from the B value as B into ln 10, and B refers to the B value of this. So with this, and M min and M max are the minimum magnitude and the maximum magnitude. So with this protocol, we have calculated, we get the probability seismic probability hazard probability curves for 10% probability of exceedance and 20% and 2% probability of exceedance. We can also have a 20% probability of exceedance and even 1% probability of exceedance. So with this, we have taken only the 10% probability of exceedance with a return period of 475 years. And if we see here, the hazard, the seismic hazard map of India with this protocol, with only probabilistic seismic hazard, with the polygonal seismogenic sources without taking the tectonic sources at all, is this, which gives a PGA variation maximum estimated PGA 1.392 associated Northwestern Himalaya and Northeast India. The cities of Srinagar, Jammu, Kangra, Shimla, Dehradun, Chamoli, Lucknow, Muzaffarnagar, Darjeeling, and Gangtok exhibit relatively higher hazard level. So is the case at the Northeast India region at the state capitals of Itanagar, Tezpur, Guwahati, Kohima, Imphal, Aizawl, Manipur, Nagaland being exposed to very high hazard level. The cities of Bhuj, Kutch, Rajkot, and Pune exhibit very high hazard level. The cities of Delhi, Udaipur, Patna, Jabalpur, and Latur are seen to experience moderate hazard to the tune of 0.44 to 0.60 G. After that, we have taken, since we already have a site class from the topographic gradient method using the IBC, the IBC nomenclature, and getting the site response of the order of about 1.5 to 2.5, varying at all the site classes. And by convolving that with the probabilistic seismic hazard at the bedrock level of BC, 760 meter per second, we have got these surface consistent IBC compliant probabilistic seismic hazard of India, which gives a PGA value going all the way from 0.48048 to 1.39 which is at the surface, and which at the bedrock was about 1.95. So this is, with this, what we do is we try to calculate the seismic risk assessment as a region at the regional level with 1:1 million scale at the Indian subcontinent, where we have considered the risk the elements are the building rural wall, building density, building rural roof, the land use and land cover, building urban wall, building urban roof, population density, spatial distribution of PGA with a 10% probability of exceedance in 50 years on IBC, and the regional seismic risk map is prepared by integrating all of them through fuzzy integration model as I'm shown out here. And this is the seismic risk map of India, which shows that the entire Himalayan territory is severely risk, and that is so is also here at the the Kutch region of the Koyana and the western Ghat mobile belt, and there is some at the southern Indian Peninsula Shield and on the eastern Ghat, and the central India is relatively has got low to moderate risk level. This is because of the urbanization and because this is also because of the socio-economic consideration. So therefore, even if the hazard level is high, the risk level is going to be low at the central and the other. Now I go into the ensembles, which is our domain, starting from west central Himalaya all the way up to northeast India, taking into consideration the Indo-Gangetic Fort-Deep, the Bengal Basin, the Darjeeling Sikkim Himalaya, and the northeast India region, including Bhutan. So what we did is we have taken the active tectonic provinces and all, along with the polygonal seismogenic sources, all the active tectonic provinces will have the activity rate of lambda f is equal to 0.5 alpha s plus sigma s n into m0, where alpha s is equal to ls by summation of ls and sigma s is equal to ns by nz, where ls is the finite is the fault length and ns is the number of earthquake associated and nz is the total number of earthquake in the polygonal sources. So with this shows the seismic activity rate at different hypocentral depth level, and with that, and this is the activity rate distribution at different hypocentral depth ranges are below 25 to 70, and this, as you see, the 25 to 70 is the one we have a huge asperity and the stress concentration where in all the tectonic tectonic fragments than it is at 70 to 180 or even more. Then after that, we have framed the projective framework for all the five tectonic blocks. This is for the West Central Himalaya, and B is for in the Indo-Gangetic Fort-Deep region, and C is for the Bengal Basin tectonic region, D is for Darjeeling Sikkim Himalaya and Northeast India. I have already explained the logic tree framework where we consider both the layered and the tectonic provinces, and then we have the threshold magnitude. There are 3, and all the ground motion prediction equations which has been developed for here. So with this, we have a probabilistic seismic hazard for the whole ensemble, and these are the probabilistic seismic this is the hazard curves with 2% probability of exceedance 50 years, with 10% probability of exceedance 50 years, and PGA, PSA, and PSA at 0.2 second and 1 second, because 1 second and 0.2 second are required for this for design response spectra. So this shows the PGA variation of going from all the way from 0.02 to 0.002 to 0.59. So this is at the bedrock level at the BC. Now we come to I now go into, so we have got the hazard at the bedrock level. Now I will put it to the surface through probabilistic through site classification. And so what do we do in the regional site classification? Allen and World has considered only topography, but we have considered here geology, geomorphology, landform, and topography all together. And so we have basically the VS30 coming from geotechnical and geophysical data, and from earth science attributes like geology, geomorphology, slope, and landform, we get the GGM, we get the regional seismic velocity coming from here. So what we consider, the entire territory were divided into training and the testing. And so the training we have considered with the multi-polynomial regression, considering geology, geomorphology, slope, and landform, and we have come up with a fifth order. I'm sorry, I just skipped this. So these are the basically is the protocol for site classification. We have 3 protocols. One is the NEHRP, one is the UBC, and the other is the latest one is the sun classification. NEHRP has got A, B, C, D, E, and F, and in UBC also has similar. But then Sun et al. Has divided C into 4 C1, C2, C3, and C4 site classes, and D also has been subdivided into D1 to D4, and E has remained as less than or equal to 180. And if E is being liquefied, then it becomes F. So this is the definition of all of them, and I am skipping these definitions. So what we did is that we have taken the Northeast India as a benchmark case study for regional site classification using the geology, geomorphology, and topography, and the landform. So what we did is this shows the surface geology, B shows the geomorphology, C is the integration of geology and geomorphology. This is the GGMP map, and then we have the slope angle coming in here in D, and E is the landform. So what it is, we have evolved a fifth order polynomial considering all the five earth science attributes here. And by doing this, we have got a regional level site classification of Northeast regional level site classification of Northeast India, which has given us 11 site classes, and even the very fine site classification has also been obtained out here. Once we correlated this with the regional, our regional, and the geotechnical, which is the in situ, we have seen that they are within the plus 1:1 with plus minus 1 standard deviation here. And but if it is compared with geotechnical with the topography, it is underestimated. And if we have gone for regional residual plot between the geotechnical and the regional, this is almost coming to the center line. But the topography and the base and the geotechnical has become negative. So therefore, it shows that it has been underestimated out here. With this, and these are our in situ the in situ data points where we have done the HBSR the survey location about 15,000 ambient noise survey. We have more than 2,000 borehole locations. We have about 1,500 MSW and SSW data and joint HYV and MSW, SSW, and in situ geotechnical locations about 2,000. So once we have, and this shows some of the glimpses of some of the geotechnical data at borehole in Chandigarh. This is a borehole in Amritsar. This is in Agra, and this is in Noida. And these are similarly in Kolkata, Damdam, and this is in Dhaka, Rohitpur, and these are in Guwahati, and this is in Gangtok. These and all these are the data which are our own data. We have dug up, except for the Dhaka, which we obtained from Dhaka Urban Development Ministry. So, and then we went into the surface geophysical the investigation by using SSW and MSW technique. I've shown you the field setup out here, and where we have either we can go for SSW and MSW single, we can have a joint fit of HBSR and MSW, or we can have the MSW a single, and which will give you 2D cross section of the shear wave velocity distribution. So this is the framework that shows the type of the investigation that has been carried out by several agencies, and also some which we have done ourselves. So these are some glimpses of the ambient noise survey. This is the raw data, and this is the H by V. And we have, when we have inverted H by V, we have got the 1D velocity structure. This is in Newtown, Kolkata. And this is a MSW survey that has also been done in Salt Lake area in Kolkata. And this has been shown for 4 different locations. This is in Kolkata, this is in Amritsar, this is in Chandigarh, and this is in Guwahati. And this is an HYV come, and this is the joint inversion of MSW and SSW, wherein we get the 1D velocity structure by combining HVSR as well as the dispersion curve. This is again a joint feed in Medinipur in West Bengal, and this is in Roorkee. And apart from this, we have considered the in situ shear wave velocity from downhole seismic survey, as well as the geotechnical NPD, the SPD values corrected, and we have developed the exponential relationship between VS and the corrected SPD N values for different lithology depth wise. And these are the these are 4 average lithology: sand, clay, silt, and all soils for combination of Agartala, India, Chennai, Delhi, Chennai, Bangalore, and Delhi for these average site classes. These are also, so with this, from SPT n values, we can get shear velocity, or vice versa, from shear velocity, we can convert SPT n values for liquefaction. So therefore, with this, we have got the site classification map of the tectonic ensemble of 5 tectonic blocks taken together. And we have 11 site classes, starting with site class E to site class A. So this is site class A out here, and otherwise we have all other site classes here. And then we have to go for ground motion prediction equations, because we have to generate the ground motion prediction equations. So we have got data, some raw data from PESMOS, from our own strong motion station, and from other stations from Guwahati, IIT Guwahati, and all. Apart from this, we have to also synthesize by using stochastic simulation. And by using stochastic simulation, we have simulated many of the earthquakes, and these are some of the sample simulations. This is for 1905 Kangra. This is for 1934 Beer Nepal earthquake at Patna, and this is Mansa, and this is a 1930 Dhubri earthquake located in Sylhet, Bangladesh. This is 1918 Simangal earthquake at Rajshahi, Bangladesh. 1897 Shillong earthquake and Gotanagar, Guwahati, and this is in Tashigang, Bhutan. This is a Bhutan earthquake of 2009. So with this, this is a cartoon that shows where the earthquake has originated, and the earthquake takes a path, and it has to come to the engineering bedrock, and through this engineering bedrock, it has to come to the soil layer, and this soil layer is what we have got from the drill hole investigations, and also the model that has been created by using both the geophysical and geotechnical investigation together. And then we use deep soil analysis for doing site response study. So we initialize, select the linear or equivalent non-linear. Geotechnical geophysical field investigation has been carried out. So we have the shear velocity layers, and then we have the recorded and synthesized ground motion, and then we have the soil parameters. These are the model, and then we have used XMSIM. We have got the bedrock properties here. So finally, we've got the acceleration time series and the acceleration frequency domain. So these are the final output. With this, we have got into site response distribution for all the site classes that has been obtained, and then these are the generic site response for the site class, generic site response for site class E. This is site class D4, this is for D3, and all of them as you go. E shows the maximum highest site amplification spectra, and as we go and come down to site class B, you can see the site response curve has flattened, and site class A is almost, this is because of the topographic effect. So this with this we go into getting the PGA. This is the surface PGA distribution at the because we have convolved the PGA at the bedrock with this the site response, and with this we have got the PGA distribution at the surface, which will vary between 0.04 to 1.23, and these are the design response factor at the surface at Amritsar, Agra, Kolkata, Dhaka, Shillong, and Guwahati. And then we go into so we got now the surface seismic hazard. Now we're going to induce seismic hazard coming from the secondary phenomena, which is a liquefaction, which comes exactly in the northeast and the alluvial and the Guwahati, Kolkata, Bangladesh, and the Indo-Gangetic Four Deep region. These are all alluvial field terrain where we do liquefaction assessment from CRR and CSR through geotechnical investigation. So we have both the earthquake data, the geotechnical data. We calculate cyclic resistance ratio and cyclic cyclic stress ratio, and then we calculate the FOS as a ratio between the two, and then we calculate the liquefaction probability from FOS as a distribution here, and liquefaction risk has been calculated from a liquefaction potential, liquefaction probability density, and the thickness of the layers, and LPI is the liquefaction potential index, and these are all other parameters. So this is, with this, we have done the synthesis of the liquefaction LPI distribution from all the historical earthquakes of 1905 Kangra for north, in the northwestern Himalaya. The 1803 is Garhwal earthquake for this, and then 1934 Bihar Nepal earthquake in this zone, and 1885 Bengal earthquake in the Bengal Basin, and 1897 Shillong, and 1950. So this shows a collage of the liquefaction scenario for the entire tectonic ensemble. And this shows the liquefaction LPI distribution in the cities of categorized as low, moderate, high, and severe in the city of this is in the city of A is in Amritsar, this is in Kolkata, this is in Shillong, and then this is in Dhaka. So this are and the same cities when we go into bringing in the deterministic liquefaction potential at the surface, liquefaction potential by using the surface consistent probabilistic seismic hazard, this shows a severe liquefaction potential distribution here for Amritsar, Kolkata, Dhaka, and in Guwahati. So with this, then we go into for the topography, the rugged terrain in Darjeeling, Sikkim, Himalaya, and Bhutan, go into landslide distribution by using spatial and non-spatial data, geological, geomorphological, environmental, this, and then we do data integration by using hierarchical method or the machine learning and the artificial intelligence, statistical analytical validation of LSI through ROC and R index, and the landslide hazard donation. So we give a case study for Gangtok, which has been we accomplished very recently based on the surface geology, the geomorphology, then the land use, land coming, and these are the slopes, and this is the PGA distribution at the surface, and this is the landslide susceptibility donation of of Gangtok, where as low marked as low, moderate, high, very high, and severe, and this shows the area under curve with ROC distribution, and this shows the R index. These are the error curve. This is also a stepwise error curve. This is how we define the error function. And so high susceptibility, and the classification is shown. Severe is way between 0.8 to 1, and very high is between 0.6 to 0.8 and 0.4 to this. And with this, now we come into, and we did the slope stability analysis by using the GeoFlow slope software of the Quake W and slope. And with this, we have got the FOS distribution here, and this shows the unit circle and the extent of the circle from where the earthquake, the landslide is triggered. And the static model has shown 1.28, but the dynamic model has shown 0.26. So with this, I now go into the implication of seismic hazard. I hope I still have a little bit time. So
5 minutes.
Yes, I am now in the last slide. So therefore, a last part of the, so with for implication of this, I have considered the Selena, which is a GIS-based Selena software, which needs a probabilistic seismic hazard at the surface through deep soil and the ground. So we have the surface level seismic hazard, and then the vulnerability and fragility curves, and the capacity spectrum method, wherein we calculate the building damage in terms of non-slide, moderate, extensive, and complete. Building construction cost we get from the urban ministry, and then the human inventory we get from 2011 census as of today, and then we calculate the economic loss, we calculate the failure. So we have actually identified 12 building typologies here, including the heritage building. This shows the height of the buildings, and these are the different stories of the buildings which are being used here. So this is where this shows the uniform hazard curve for each and every city here, and this is the capacity this is the capacity curve. So the capacity curve intersects at the uniform hazard curve at a point, and at this point we get the spectral displacement, and once we take the spectral difference in the fragility curve, which has a complete extensive, moderate, slight, and none stage of failure, this shows what is the extent of the damage. So this is called the capacity spectrum method, and these are the 5 state of failure we get: none, slight, moderate, extensive, and complete. And this is a fragility curve here. So this shows the capacity curves for all the 11 building types, excluding the heritage building here. And these are the fragility curves obtained for all the 11 buildings except the heritage building out here. So with this, we have got the deterministic structural damage scenario for Amritsar for all the 11 the 11 model building types. And this is at Agra, this is in Kolkata, this is in Dhaka, this is in Gangtok, and this is in Guwahati. So with this, you can see what exactly is the type of the hazard implications in terms of the damage distribution. And if we go into the human casualty ratio, in Amritsar at 2 a.m. in the dead night, the seismic, the casualty will be extremely high. And this will be at 10 a.m. it will be this, and at 5 p.m. it will be low. And here, this is in Agra, this is the Kolkata, Dhaka, and this is Gangtok, and in Guwahati. So we can, with this, we can see what exactly is the implication of the hazard. So I have given you, basically, therefore, I have given you so I have given you the total journey. We have taken a journey through the seismic hazard and risk of the Indian peninsula as a whole. Then we have taken the ensemble of the 5 tectonic blocks that takes from the northeast and northwest Himalaya all the way into northeastern India region. And India being considered as one of the most hazard-prone country in the globe, in the globe, and all these 5 tectonic ensembles have been also considered based on their type of the hazard distribution. So now we can, if we come to conclude from this discussion, seismic hazard analysis has emerged as an important issue in the high-risk urban centers across the globe, and is considered an integral part of earthquake-induced disaster mitigation process. And in practices, site conditions significantly include seismic hazard potential of a region, and therefore its characterization is of utmost importance in the quantification of site-specific surface-consistent seismic hazard of any earthquake-prone province anywhere in the globe. And the present study appraises the site characteristics vis-a-vis the site-specific seismic hazard potential of the ensemble of 5 tectonic provinces, West Central Himalaya to Northeast India, including Bhutan, Indo-Gangetic Four-Deep region, Bengal Basin, Darjeeling, Sikkim, Himalaya, based on an enriched surface geological, geomorphological topography, landform, and in situ downhole geotechnical, geophysical data base of the region, with a new regional 5th-order nonlinear power law polynomial combining shear wave velocity with geology, geomorphology, landform, and topographic gradient as a set of new lithology-based depth-dependent SPT value derived an in situ downhole seismic measurement yielded shear wave velocity. Deep soil-based nonlinear soil structure interaction, earthquake-induced liquefaction and landslide potential, and Selena Hajuz-based historic maximum earthquake and surface level probabilistic seismic hazard triggered urban impact assessment on some capital spiritual commercial cities like Amritsar, Agra, Kolkata, Dhaka, Guwahati, and Gangtok belonging to these 5 tectonic provinces, which brings in a unique textbook like regional local hybrid seismic hazard disaster model for pre-disaster preparedness in the form of updated urban bylaws and post-disaster rescue, relief, and rehabilitation. At this juncture, I would like to acknowledge the contributions of the Ministry of Earth Sciences in the form of funding that has been given to us for the continuously for the last 25 years in the form of projects, and even for in authoring seismic handbook, microzonation handbook, and the manual. And also this is an output we have got for the probabilistic seismic hazard for 40 cities that has been generated by us as a part of a mission MOES mission of the seismic microzonation of 40 cities. So with this, I come to the close of this, and I also acknowledge the support I got from my students, my colleagues from the Ministry of Earth Sciences, from MOE, from Jadavpur University, I.I.Sc, Shibpur, and all other places from where we have got this, and the Dhaka Urban Ministry, and the Dhaka Geological Survey of India, Ministry of Earth Sciences, IMD, and the Geological Survey of India, also IIT Guwahati and the and IIE and also the Jorhat the NEIST Jorhat, I suppose it is called, and the Wadia Institute of Himalayan Geology, and all my colleagues who has helped us to come up with this results. And thank you very much, the 7th International Conference organizers, for giving me an opportunity to present my case house here and make a presentation in the form of a keynote address, and also publishing this in the keynote address volume. And I think this has become a benchmark case study for anybody who will be taking up this kind of study, starting from site classification all the way into disaster modeling. Thank you very much once again for giving me a platform for presenting my thought. Thank you very much.
Thank you, SK Nath ji. It was excellent presentation and a lot of work.
Thank you, sir.
Half of the India, I would say, is not easy. It takes really hard work.
Thank you, sir. I appreciate your kind words.
So I would two, three questions. The first question is from my side itself.
Yeah.
Because I stay in Delhi, so you showed that the Delhi has the acceleration levels of 0.44 to 0.6 G.
Yes, that's right.
On the other hand, our codal provision and all our designs we are doing with the 0.24 G.
Yes, I know that.
So what are the implications of this, and what means, I don't know how to comply with these things now.
Actually, if you now allow me to respond to you. If you look at the probabilistic, we have the seismic microzonation microzonation atlas of Delhi was also published in 2016, I remember, along with the Kolkata. And if you see there, Delhi is no more in most part of Delhi. The entire Delhi is not, of course. Here you will get Delhi as a point. But once we have the microzone Delhi, part of the Delhi, the East Yamuna sector, and part of Delhi towards the West Central Himalayan part, those are no more in 0.24. That is, and 0.24 is basically the zone 4 of seismic zonation map of India of 2002. But those are, the microzonation has put Delhi into all the zones now. Some part of Delhi is in zone 2, some part of Delhi is in zone 3, some part of Delhi has also been shifted to zone 4. Zone 4 means, see, Jamuna, East Yamuna, where lots of urbanization is going on, it is highly liquefiable zone. So if you look at all the hazard aspect of it, including the liquefaction, including the geohazard and all, and it is not only the seismic hazard, but the seismic hazard with the geohazard, once you take both of them together and integrate them judiciously, you will see the holistic hazard level changes drastically. So this is what we have to do. This is the next level science of urbanization. So this is the reason why we have the microzonation is as a consorted project is being taken up by Ministry of Earth Sciences, and they have already started it. And I think they've given 14 cities are already being under investigation for seismic microzonation, and this is the essence of it. So I have not shown you microzonation. I have only shown you the hazard. I have only shown you the hazard level, but not the microzonation.
Okay. Yeah, but do you think that one should start designing?
Yes, yes. Now the time has come. It is, sir, now the time has come to look into the, even in Kolkata, I have the atlas I have given. The Kolkata, you know what is the fun is, the Kolkata was been put in between zone 3 and 4. So these guys, all the urbanization and the skyscrapers, they are coming up, they are taking zone 3 as the design for their design level, and zone 3 is a 2.24. So and now, and when we have microzoned it, now Kolkata has been microzoned as 2, 3, and even part of it is in zone 4. And this is the thing, and nobody wants to do this. And you will also be surprised to see that they are not doing any geotechnical investigation that has been required for all the high-rise buildings and the skyscrapers. They're using thumb rule, and they're using the old data, and also using the design response spectra as has been given for 3. So this is the reason why microzonation has been taken on war footing now, and this is also the reason of putting the input in the smart city the urbanization process.
Okay, thank you, Professor Nath. And I would. There are 3 questions, so I would request you to be brief in answering.
Of course, I will.
Yeah. So first question is by Sri Valsa. He's asking how reliable are below 3 methods. One is slope as a proxy for site amplification, Allen and Wald method. Second, applying site amplification factors for different site classes, VS30. And third is ground response analysis using geotechnical data and VS30.
Yeah, you see, geotechnical investigation cannot be done all over. You can understand the cost involved in this. So we try to go into a cost-effective method. We go for surface geophysical method, then geotechnical investigations. Maybe the geotechnical investigation will be about 20 to 25% of the total investigation. The remaining, you can go with geophysical investigation. Even in geophysical investigation, everything cannot be done. So that's the reason why we have 3 sets of relationship. One is taking geology, geomorphology, and the landform, and also the topography, because only topography is not enough if you are trying to take the alluvial field. And only geophysical is not enough. So what we have done, we have 3 levels of investigation. One is SPT and the shear wave velocity conversion. The second is the surface to subsurface geophysical investigation. So you understand, we have a surface geophysical method and the subsurface geophysical method, Borol. So we have a conversion there. We have subsurface to SPT. That conversion also is we have developed, and we also have added geology, geomorphology, and landform to improve Annan Wald's technique and make it to a 2nd generation technique where all these attributes are going in. So we have, if we use all of them together, I have shown the residual curve. I have also shown you the 1:1 correspondence plot where I have shown that if you're using all of them, and if you're using only Allen and Wald, so where it is happening. Allen and Wald is underestimating, and exact is geotechnical if we take, because this is in situ. And if we take all other parameters together, so they are coming very close with a 1:1 with a standard deviation. So I think with this much of variation, because this is not a very rich people science and engineering, because this is very expensive, and this is very inclusive and exhaustive process. So therefore, we have to come up at a level where we use all of them together to reinforce the result of one with respect to the other.
Thank you. And the next question is by Aniket Desai. He is asking, in central seismic gap, that is Garhwal Kumaon region, the probability of large earthquake, that is MW greater than 8 in next 100 years is 0.52. Possibly causing millions of deaths. What steps can be taken as prevention in terms of codal provisions?
The codal provision will be as per the design response spectra that comes up with either 10% probability of accidents or 2% probability of accidents. With 2%, we cannot take, because that gives a return period of 2,475 years or 2,500 years. And with 475 years of return period, which is the conservative estimate we use all over, because 500 years is the estimate that we are using all over. I think this gives a better estimate of using the maximum credible earthquake in this region to go into normalizing the design response spectra in that particular block, because this is also a seismic gap there. Okay. We have seen 1934 Bihar Nepal earthquake coming in. We have also seen a Nepal earthquake of 25th April 2015. and there are earthquakes coming from there, and then we have 1988. So therefore, there is no other way other than going into MC, and MC is 8.3 as I have shown over there, with 500 years of return period.
Okay. And the last question is, as there are lots of uncertainty and possible errors involved in testing and inverse analysis for geophysical and geotechnical tests, how much they would alter the results?
Actually, we have used three techniques into all together. One is the machine learning and artificial intelligence. The one is a heuristic approach. The other is a fuzzy technique. So once we have taken these three techniques and then we correlated with respect to one another, we have seen the final integration of using the artificial intelligence and machine learning that gives with 95% confidence level, whereas the fuzzy and the fuzzy the technique gives you 87% confidence level, and the ROC is about 0.823. So if you, what we have to do is, because the entire work, entire amount of work is with lots with ambiguity, so therefore we have to adopt several approaches and try to see that all the approaches are going towards the same direction, and see how the results can be coming and getting focused with the minimum error together, and get the information obtained from all the 3-4 processes integrated together, and then finally increase the uncertain confidence level of the results that has been presented, and not only presented, published, and also handed over to the Urban Development Ministry for implementation. This is very important out here.
Thank you, Mr. Nath, Professor Nath. And with this, we thank you, and I invite Professor Amir Kenya for the next presentation. And
thank you very much. Thank you.
Dr. Arun Gupta, please.
Yeah. Thank you, sir. So, Professor Amir Kenya is a technical expert in vibration and earthquake engineering at NGI and adjunct professor at Department of Structural Engineering, Norwegian University of Science and Technology. He has received his MSc and PhD degree in structural engineering from Massachusetts Institute of Technology. His area of research and practices include earthquake engineering, soil dynamics, and soil structure interaction. He has published more than 170 papers in peer-reviewed journals and international proceedings, and has held numerous keynote lectures worldwide. He has participated in many research projects funded by European Commission, coordinated 3 major projects funded by European Commission, Norwegian Council, and Joint Industry Initiative. In addition, he has led many national and international offshore and onshore industrial initiatives as a project team for revision of Eurocodes 8, Part 5 of Geotechnical Earthquake Resistant Design. He is also chairman of Norwegian Earthquake Committee for National Standard. So with this brief introduction, I invite Professor Kenya to present his keynote address on high-speed trains with different tracks on layered ground and measures to increase critical speed.
All right, this is the title of my talk, high-speed trains with different tracks on layered ground and measures to increase critical speed. This is going to be a summary of the topics I will talk about. Vibrations generally in railway projects, historical note, what is critical speed, field measurements, some numerical modeling technique, and how to use techniques to reduce vibrations against these on these tracks. Basically, the challenge is that we have now railway challenge coming into urban areas with high-speed line coming closer to congested areas. You could have then soft ground. You could have areas that are prone to vibration requirements, and it could be like high-rise buildings, which actually makes the situation worse. So vibration is becoming actually more and more a serious problem in urban areas. Vibration generally increases due to rail and track and ground irregularity and wheel damage, what we call wheel flat. For the same conditions, vibration increases as the soil gets softer. When we say softer, we mean in terms of stiffness, shear wave velocity, shear modulus. And vibration at the same time increases with train speed. All these are intuitive factors. In many cases, for example, in Scandinavia, very much north of Europe, we have soft soil, so soft that even ordinary high speed when we say like ordinary is like 200 to 250 kilometers per hour, they reach what we call Rayleigh wave velocity in the ground, which leads to a condition as we call critical speed. Loosely speaking, it's like well-known way of saying it among engineers, for which the track and ground vibration dramatically increase. I have a video I will show you. You will see how it works. And in many countries, of course, please realize that when we say high speed, it's easily reaching 400 kilometers per hour. But in many countries with soft soil conditions, areas, even 200 to 250 could be problematic. I have in the written version of this talk, in the proceedings, in the book, some historical note on the problem of moving load. It's like 2D solutions. I have a list and the history of the 2D solutions from many authors with many different techniques, theories, potential theory, Fourier Laplace theory, Helmholtz decomposition, and you name it. Most of the theoretical development were indeed done before 1970s, and a good work by Professor Friba in 1973 nicely sums them up. And then 3D solutions, of course, more naturally are more important. I'm not going through these, and they have evolved over the years, and they are mostly theoretical until, and okay, I will go next pages to numerical. These are all mostly theoretical solutions. And then there are some terminology defined by Cole and Huth. They call it Mach numbers, that it's when you divide the pressure wave velocity and shear wave velocity by the train speed, they are called Mach numbers, Mach velocities for train speed, and you will see why. Now, when we talk about high-speed lane, it is sometimes common. It is common to refer, when the speed is very high, to speak of subseismic, superseismic, and transseismic, borrowing terminology from aero industry, aerospace, and it has to do whether the speed of the train is less than the railway velocity, greater than it, or greater than the pressure wave velocity. And this image from the pioneering work of Barros and Luco shows what the situation is. The train is moving, this is a simple load on a layered ground. As the load moves in this direction at low speeds, it just wherever the train arrives, there will be a large displacement, and then it disappears afterward. As the train speed increases and it's moving still in this direction, then suddenly we see the formation of these Mach lines that represent large displacement in front, like plow lines, bow lines, like a boat on water. That as it moves, it creates these bow lines behind it. Pretty much the same. I have a video soon showing you shortly that it shows. And as the train speed, still the train is moving in this direction. As it is moving faster, these bow lines actually bend further back and start to make some features also in front of the load, until we even come close to the pressure wave velocity of the region. And then another Mach line is created. So it's a very complicated pattern of displacement is created. Now, while these theoretical solutions were going on and were presented, it was not until 1998 when evidence of this critical speed and large displacement were observed in test runs at a test site in Sweden. thanks to the work of Swedish Rail Administration, courtesy of them. The site was, because they observed a lot of response at this site as they increased the train speed, which previously did not have any problem. And when they did a good site characterization, it turned out that they found like an organic peat layer with very low shear wave velocity, about 2.5 meter, shear wave velocity of the order of 30 to 40 meters per second. And it's a good combination. They all corroborated and characterized the site. And I show this is going at about 140 kilometers per hour, and the camera is heavily moving. This was digitized after 1998, and then the quality is not as good. So I have a more recent one. This is more recent, like 3-4 years back. And when the train passes, pretty much watch here, because nothing happens until the train comes here. It is slow motion, of course, and you will see wave generated depending on the speed of your receiver. You will see waves generated on the ground. So let's try that. I tried again here, look at here. So basically, this is like a, let's say, animation of the same case. As you see, the train is moving this direction, and these plow lines created as the train moves, and then it creates what creates vibration. What is the critical speed? Main features of the response is that we see a drastic increase in response as critical speed is approached. There is going to be a dynamic amplification. Amplification reduces above critical speed, so that's why it is called critical. Dynamic motions upward and downward happen. At low speed, there is no upward motion, it's only downward. But when you reach this speed, you start to get even the track is vibrating up and down. A plow-shaped wave fronts, called Mach fronts, on the ground surface appear as this is moved. There are, as I said, I had a summary of theoretical solutions, but more recently, because people want to have all the features of the train track, layering, even non-homogeneity, heterogeneity, everything. So mostly the solutions have been around finite element solution, combination of finite element, boundary element, Green's function solutions. Some people use what we call 2.5D finite element, which means like just a slice of this element and then using Fourier transform in the other direction to make it faster. So these are like examples from the literature with the references underneath them. This is like a full finite element with good boundary conditions. If I'm not wrong, it is Abacus, if I'm not wrong. And these are like cases that you get the response by superposing the response from individual loads. And this is the model, the 3D model in COMSOL we tried at NGI through this paper that shows the complete model. It has PML limit so that we do not need to have very large model. This is the section. And this is the section. So a lot has been done recently. And we have another model for filtering, for screening and for capturing the mechanism of like wave propagation in general, that it is based on a track modeled as a beam and on a layered ground. And it is through a kind of a decomposition method that the load interaction between the track and ground is like if it is called P, and then the ground response of the ground is expressed through what we call Green's function, which is the displacement at all these points as a result of these loads coming. And then the track model, the track itself by a finite element is straightforward. And then, of course, once you put them together, you get the complete response of the system. So this F is related to the stiffness of the ground and the stiffness of the beam. And this is solved in the time domain. And when we say Green's function, it's like the solution at all these points due to a unit load. And it's usually, there are analytical solutions for them that are solved numerically by time integration numerically. So we used that one when we were involved in this research project, and this shows some of the simulations and some of the measurement. What you see here is like the red is the measured values. This is like at one point of time, consider it that you freeze time and you take a photo of the displacement pattern. So this is like the train location. These are like the axle loads, and you will see that the displacement is as expected. It is like the footprint of the loads. So everything is like positive downward or negative downward. And the simulation in blue is pretty much nicely matching it. Everything is, of course, downward. But as the train speed increases 185, you will see the pattern completely changes. It's not like wherever the load is, like the displacement is maximum. And then we look at that moment of time, the displacement along the track is pretty complicated. It's upward, downward, it has a vibration pattern in it. And of course, we did not have the result for critical speed because they could not do the test. So these two are only the result of simulation. So if we plot all this data on a graph with train speed on the horizontal axis, as the train speed is low, let's say even up to 100 kilometers per hour, this is the curve for upward displacement of the track, and this is for the downward. Basically, there is practically zero upward. It's all vertically moving downward. And there is like a lot of like up to 4 millimeters in this case. And as the train speed increases, you will see that not only this one increases the downward, even we start to get upward displacement. This is the feature I explained to you. And there is a point that we loosely call critical speed when the maximum displacement is achieved. More theoretical solutions have done it mathematically by presenting critical speed in terms of group velocity of the continuum, like several researchers have done. The most recent is by Professor Hausel of MIT, and very nicely presenting this critical speed in a mathematical sense. But for engineering purposes, this is easier to visualize, that the point where the maximum displacement is observed. And just to be sure, this COMSOL model is doing this a good job. This is model from the top. The load is moving along this direction. You will see these are the colors of the displacement. These are the Mach lines generated like this as the load is moving. And this is like a 3D pattern. As you could see, displacements penetrate into the ground, same fashion, and also as the load is moving on the two sides. This part is like the PML, so that so the model is actually pretty small. It's only this part, and everything around it is like this absorbing PML, so-called PML model. Now, having said all this background, what do we do? How do we deal with, now we could have vibration problem. How do we deal with it? So there are different ways. One is at the source, under the source. Somehow we should fix it here. The other solution is that we stop it on the propagation path. And then the other thing is at the receiving point, either in the building by making it stiffer, whatever, or like in the foundation, for example, making it stiffer, putting piles, again, whatever solutions. So there are different ways of dealing with these vibrations, and they depend on the type of vibration. Basically, there are two regimes when it comes to ground vibration from trains. One is usually at high frequency, and they are these high frequencies. When I say high frequencies, like over 20 hertz, 25 hertz, pretty high frequency. They are usually created due to rail or wheel unevenness, corrugation, being defected wheel, or cracks, flats. So these are usually or the track being not perfect. So these are usually handled often by 2D models. This is a 2D model. The load is perpendicular to the plane. And this is if there is, like at a given frequency, I'm just showing it qualitatively, one case just, and it shows the ground vibration from, I forgot exactly what frequency, 20 hertz or something, what pattern we have. And then this is like after putting some countermeasures, like in form of trenches or stiffened ground. And you will see what it does in this case is that it returns the vibration, basically reflects them back. And this area, which is mostly for residential and other purposes, is protected. So this is one type of countermeasure, which works for usually higher frequency. But when we come to critical speed issue, which is a problem that it's created basically at the source, and basically putting such things, it doesn't help because this is lower frequency and these measures usually are very ineffective. So and also one has to do something with the track, otherwise the track will be in trouble. So there are like how to deal with them, and these are like happening many places. The most recent of them, you see the project HS2 in UK. In some areas has to deal with it, for example. There are different solutions. One of them is actually ground stiffening, let's call it, or ground improvement. One of them very popular in Northern Europe is through lime cement column, which is like mixing the ground with cement as it is extracted soil. And then you basically at the end make a series of stiffer soil, half concrete, and make the ground stronger. It's very, very fast operation and rather cheap actually. So this was tried at this site that I showed the video to you that had this problem. It was performed at that one. It was 2 lines, so 1 line was removed, only 1 line was used, and then during that time it was applied this technique, as you could see how it looks in some, and it was penetrated through that peat layer, and some of these columns were driven further down, and it turned out to be very effective. The red is like the displacement along that as the train was passing. You could see like large displacement, like over 1 centimeter. And after, this is before and after this countermeasure, it was dramatically reduced to almost nothing. So it was pretty much effective. And we did simulation of it in COMSOL as well. I'm not going to show you, but I'll show other type of results. Now, the question is back to the same thing, the issue of critical speed, how to increase it. Because the best way, the only way to avoid the problem is like, it's not like having trench next to the track or something. You need to do something at the track. And the solution is basically to do something so that this critical speed is increased, so that we are not getting to this area, basically pushing this to the right. And how to do it? In my paper, I have investigated 3 methods. 3 cases I have considered. The first case is stiffening the ground. Okay, this is this one. It's the opposite order. The first one is the second one. Let's say stiffening the track and embankment, like putting a stiffening embankment, or even putting a very stiff beam underneath the track ballast and all that, and making it stiffer, which intuitively makes sense. And as the train goes, it just distributes the load better. The second one is stiffening of the ground. So rather simply replace a part of the ground by some improved material, by some better material like crushed stone, or injection and grouting. There are many techniques, soil improvement basically, or use of piles. So basically put the track, whatever it is, a beam or whatever, on a series of piles. It could be one pile, it could be several piles, but anyway, in the area, because this problem is not necessarily everywhere, it's like certain stretches, and then it could be done this way. Pile driving is simple, so this could be done rather easily, and it's very reliable, because then you are sending all the loads to deeper layer rather than being worried about gradual settlement, effect on it. So each of them have advantages. Now, to measure the performance of these methods, I first look at my base case, which is no measure, which is the case I showed through the video. And it is the site with this organic layer, soft soil. These are the train loads, exactly as was used in the test runs. And these set of figures are displacements. And these are the corresponding, so they are the same information. Ground velocity on the track, particle velocity, and this is displacement. You just need to think about this one. These are different speeds. This is time. So as the train passes, and we look at a given point as the train passes. So when the load comes, this pattern of displacement is observed at a given point as a function of time. So this is at low speed. So this is as we expect, low speed. But as the speed increases, the pattern starts to change, and then completely changes, goes to this super seismic and trans-seismic and others, like track moving upward and the vibration. And numbers are dramatically larger. This is like below 1 centimeter. This is already over 2 centimeters. So this is what I call as base case, as the case was there, because we have numbers for it, we have data for it. So the first case is stiffening of the ground. This is ground improvement. So what I did is that I replaced, this is a very effective method and could be reasonably done. It could be different ways. As I said, it could be injection, grouting, or it could be replacing of the material. So and in this case, I replaced it. The peat layer was completely replaced. That's the problematic layer, natural. So this was what was done. And this is like the base case. I just copied it here for reference. And same velocities. And now with the new track, let's say track is the same, it's just the ground is changed. You will see that, please note that it's not the same scale, by the way. If I use the same scale, these figures would be very small. So this is like much smaller. For the same speed, displacement is considerably smaller. Look at this one is 0.003 and this one is 7-8 times. So definitely it is a very effective technique. Of course, in each case, as you increase the speed, vibration, displacement, and vibration, acceleration, speed increase. But if we use that one as a measure, it is an effective technique. And of course, then one could go ahead and optimize. If you have a good technique, like the tool I showed, VipTrain, you could easily optimize it, like how much, because we don't want to make it too stiff. Too stiff has its own problems, actually. It has problems for higher frequencies. So it's a balance, how much we want to make it stiff. So yeah, so this was a very effective solution, and it's very reliable. Just to get an idea, because from this figure, we see that we are not getting anything close to critical speed of the new system. So that means that we have succeeded in increasing the critical speed, because it's nothing happened. So what is, if we want to see what has happened with the critical speed of the new system? So what I did is that I basically increased the train speed, and I computed the ground displacement as a function of train speed, maximum. And we will see that, as the train speed increases, there in those simulations, I stopped at 300 kilometers, but you see that you increase. At about 450 kilometers per hour, you get the maximum response. And then after that, again, it reduces. This is what could be loosely said as critical speed of the new system. And we are, of course, if the speed is design speed is like about 40% lower than that, like in this range, it's a success. It's a good solution. We're way away from it. So this is that one. But then the other solution was track stiffening, because people could say, well, this is easier. We just simply make a stiffer embankment on the ground. We don't need to touch the ground, or maybe even put a girder beam, a stiff beam, underneath the ballast and make it stiffer. In other words, the track is stiffer. So again, I'm showing only two speeds. For example, use of stiff beam. I'm showing just two cases. One is the base case. This is the same before, the two speeds, and stiffened track. When I say stiffened track, I mean the results for stiffened track are when stiffness of the embankment or the beam together is in the base case is quadrupled, so 4 times. So and 4 times. So we see an improvement. It's the same scale in this case. So we see an improvement. However, when I see this upward movement, there is a good improvement. But when I see this thing, it gives me a bad feeling that maybe I have not fixed the critical issue. So it has helped, not dramatically. Stiffer track reduces the displacement and vibration, fine. But they do not noticeably change the critical speed, which I'm going shortly to tell you, because I see this feature of this upward movement. Displacement reduced is not necessary. And how can we judge it? If I look at ground response 10 meters from the track, away, track side vibration. Now, this is the original track. So I get like typically, let's say 4 millimeters. Yeah, but you see this feature? It's really vibrating because of this Bach lines and plow lines, moving. So it does vibration. And when I look at the case, the same for stiffened track, it is reduced, fine, but we see all these vibrations again. So first of all, the amount of reduction is not dramatically, whereas the previous solution was factor of, 10, 7. Here is just maybe 20, 30%, and it is vibrating. And we should realize that this is not good, because if this is in an urban area, the houses around start to feel this. So even if the level of displacement of the track is okay, this is not at all a pleasant solution. Finally, the solution of piled track. If I put the same track on a beam and the beams are on a pile, so in this case, I chose just arbitrarily, just to get a feeling, 2-meter diameter piles, concrete piles, 9 meter long, so that they penetrate through that soft layer and then a little bit to the good layer, and installed at every 12 meters. It's arbitrary just to get a picture. And this is again the base case. And this is like, again, same speeds, but with the vibrations on the track of this case with pile track. And you see it's not the same scale. Vibrations are dramatically reduced. Now this one, for example, at the critical speed, which is the issue, is dramatically reduced. Again, look at it. I mean, it has vibrations, but it's dramatic. So it is a very effective solution. It works very well. What I'm not showing here is that, and it is in the written paper version, is that vibrations can be reduced dramatically at close to the piles, where the piles are. But resonance of the beam between the piles could cause large vibration at mid-span. This is not the critical speed issue. It's because the beam in between could go into dynamic resonance. So a design optimization is required. Maybe a stiffer beam, maybe closer piles, for example, smaller piles, but closer, that sort of thing. But at least it is a very effective solution. It has the advantage, extra advantage, that you pass on the load to deeper area that has less settlement. So it is in a way a good longer term solution. And that brings me to the summary, that there are basically 2 response regimes when considering reduction of ground vibration from high-speed train. I said these 2 regimes are high frequencies, basically has to do with irregularities of the train, of the track or the wheel that causes higher frequencies. And then we have, for that one, there are other solutions. That's not the topic of this discussion. But then it is below the critical speed, which was the focus of this talk. It is high frequency. Yeah, below high frequency, then we could reduce those high frequency response. But for this critical speed, yeah, this is the one I'm trying to say, actually. These 2 are basically the same thing. We are still below critical speed. but it is high frequency is the issue. If the train speed is close to the critical speed, the only solution then, it's not like trenches or other thing, is that we should reduce the response. To reduce it is to increase the critical speed itself by ground improvement like stiffening it or use of piles, but not by track stiffening, not just putting like a stiff beam on the track on the ground. So it has to be something inside the ground to change the characteristics of the propagation medium. And track stiffening will reduce the track vibrations, but the vibrations away from the track, like trackside, are not noticeably affected. And it is important for design of tracks on soft soil through urban areas, because now residential areas or sensitive facilities come very close to the track. So even if you reduce a little bit of the track vibration, the vibration is there to the surrounding. And then that brings me to the acknowledgement. I have to thank many projects that have contributed that this has resulted in this presentation. European Commission project SuperTrack, Swedish Railway Administration project, through several projects that continued after those test runs. I should thank them. Again, the recent European Commission Horizon 20 financial project, Destination Rail. Many colleagues at NGI, I just mentioned a few, Karin, Noren Koskriv, Christian Matsus, Junsan Park, and Jörgen Johansson for collaboration through these projects and giving various input. And I think at the end, I would like to thank the organizers of this conference for inviting me for this talk. And in particular, Dr. Ravi Jacob, because he has been my direct contact all along and has been patient. And of course, the conference team that has done a fantastic job for being very organized and making it easy for us presenters. Thank you very much for your attention.
Thank you, Professor Kenya, for your very informative and knowledgeable presentation. So, as I understand from your presentation, that operating or critical speed is more like our resonance in the dynamic system. So usually we have designs which are based on strains, displacement, or stresses. So when your trains reach the critical speed, then your displacement increase disproportionately, and that lead to accidents or problems in the passenger comfort, etc., and the neighboring structure. The only thing missing was how this VS can be incorporated in real design. That aspect could be a further development in this field. So with that, I will look at the, there is one question presently. Actually, you have already answered a lot of questions, so I don't have to speak many questions, but the question is from Mr. Harsha. He says, how the soft ground can be treated when excess pore pressure changes abruptly due to train dynamic load vibration.
Yeah, that's a good question.
This excess pore pressure over time results in huge settlement and more maintenance cost. Is PVD helpful in this scenario?
Yes, no, it's a very good question. Realize that at the end of the day, we have to make sure it's not like earthquake. We have to make sure that the ground vibrations are reduced. We are not going to allow trains go at critical speed. So basically requirements today are to avoid it by 40%, like 60% maximum. So once we get to that point, then we have avoided critical speed. I mean, otherwise the track will be damaged, deteriorated quickly. So once we avoid that, then that means that the vibrations, and as I explained, the vibrations will be reduced. Then it's correspondingly the strains and the other things will be so much reduced that the pore pressure buildup will be very much diminished. So the chance for pore pressure buildup will be, it's not earthquake. The strains are not at the level that it brings the pore pressure. And even if there is a special soil that for some reason could be doing that, then one should do other solutions like drainage or other systems, so that, because I think once you avoid these things, you do not hit this problem of pore pressure generation. If at all a case exists, then one has to find replacement like sand drains, like the solutions that we have in earthquake engineering, so that the pore pressure, if it is generated, dissipates quickly.
So just I was wondering that the tracks in European tracks, most of the this high-speed tracks like your TVG and other tracks, they are mostly on the ballasted track or on the concrete tracks. Which type is mostly used? And
Yeah,
the proportion.
Yeah. No, I don't have exact percentage between them. The dominant one is still ballast track.
Ballast.
But then, of course, ballastless, like slab track, we call them slab track, are being experimented and being used. You know, we have it in Germany, we have it in the Netherlands and other countries, and depending on stretches, they are being tried. Ballasted track are the most convenient in terms of repair, because gradually when there is settlement and other things, you know, they could go there and tamp it so that you get back the flat aligned ray. So that's why it is preferred. But of course, yeah, I don't have exact, my gut feeling would be factor of, I don't know, 20% to 80% between the two. It's just gut feeling.
And any advantage of the flexibility of the track also, because ballasted tracks are flexible compared to
Yes.
slab track. So
Yes.
any advantage in terms of wear and tear of the
Yeah, that is actually another good point. You know, as I said somewhere in my talk, if you make the track, of course, these slab tracks are not very stiff. They are not very stiff. But anyway, just to give you an idea, when you make the track too stiff, then you bring in high frequencies and there is more problem for fatigue damage. So that's like the wear that you mentioned. So that these are like all these elements in play, that one is maybe still preferred over the other one. Of course, the slab track has the advantage that it evens out the stress solution, especially for soft ground, and it is easier to construct. It's like these slabs are installed. So it has to do with also the supplier chain and the what system has more, like, let's say the construction industry is more prepared for it, has better experience, the prices and all that. But anyway, as such, it's not like slab or ballast is chosen because it is a better solution for wear and that sort of thing. It is like many other factors. But as I said,
so
yeah.
when you are saying fatigue damage, it is with respect to the second regime, that is the unevenness of the track, isn't it?
Yes, correct.
Okay.
Correct. Yes.
Thank
Because
you
if it
so
is
much.
If it is a perfect track, nothing happens. There is one question, if you want me to answer: how can we identify resonance during numerical modeling? Well, I don't want to call it resonance. It is actually a wave propagation phenomenon. When the speed gets to a point, it looks like resonance. It's not really. So numerical modeling, the easiest way is when you do finite element, for example. You can, if the finite element is robust, good model, you can increase the train speed and run for different speed. You will see that gradually as you increase, your response also increases. It is a very engineering good approach. And at one point you see that, oh, it comes to a peak, and then after that, and then you will see at the same time, track is definitely together, it's going up and down. And so this is like, if you call it, the term is resonance, if you want to call it, this is the way in numerical modeling you can identify how far you have come and are you away from it.
The only thing is here you cannot operate on the other side of the peak, other side of the critical speed. Like in
Yes, yes.
you can operate on the other side of the regional,
Yes,
but here
yes.
you have to be on the one side only.
Yes, yes, absolutely.
So thank you very much, Professor
You're
King.
very welcome.
Been very informative and very nice presentation.
You're very welcome.
Thank you so much.
My pleasure.
So with that, I hand over to Professor Ravi Jhakka.
Thank you, sir. On behalf of organizing committee, I thank our esteemed speakers, Professor S.K. Nath and Professor Amir Kenya. I must tell you my brief interactions with them. It's a really wonderful experience to work with both of them. And Professor S.K. Nath is always used to be very prompt in responding. And he's the first one to respond to my mails, proofreading, or whatever. And we all have seen his energetic presentation. And the same thing, in every aspect, he's so energetic. And though he's a topmost researcher in India, but he is down to earth man. He speaks so nicely and so politely, even with me, like juniors like me. So thank you, sir. I really enjoyed my interactions with you. I'm very grateful to you, sir. And
thank you very much.
Thank you, sir. And my experience and interactions with Professor Amir Kenya started even before this conference, maybe 10 years back. And he is very friendly with particularly Roorkee and I.I.Sc, Indian Society of Earthquake Technology. He is supportive of all the activities of I.I.Sc. Even now, when we requested him to deliver keynote, he immediately accepted. And in fact, he is in the middle of his vacation. He took break from his vacation for the delivering this lecture. Thank you, Professor Amir Kenya. Thank you very much.
You're welcome.
Thank you very much, Professor Ravi, for everything. And you had been really great. And you have been very patient. And I think our collaboration for the whole of the conference went very well. And we have developed a very good relationship among ourselves. That's very important. Thank you very much. And I hope that you prosper and you do well. And in future also, I think we retain this relationship and we go ahead with this, because IIT Roorkee is one of the greatest institutions and doing fantastic in geotechnical earthquake engineering. And this is, I think, one not all like others. So therefore, with this, I again thank the organizing committee. Thank you all very much for this opportunity. Thank you. All my best.
Thank you, sir. Thank you for your well
God
wishes.
bless you. God bless you. And your daughter is also a very nice performing artist. So therefore, please encourage her. And we in future would like to see her live. Thank you. Thank you very much. God bless you, your family, everybody, and all my colleagues, Professor Shitaram, Professor Maheshwari, everybody, all the colleagues and all your team members. Thank you. God bless you all. Okay.
Thank you, sir. Thank you very much. Because of all of your cooperation, and we members of organizing committee are able to do well this conference, sir. And we also very much thankful to our chair, Professor J.T. Sahu and Dr. Arun Gupta, for kindly accepting our invitation and chairing this session. Thank you.
You are welcome. You are welcome.
Thank you.
Thank you.
And before we wind up this session, we have a few announcements. One is regarding the exhibition hall. We request all our delegates to visit exhibition hall. There are a number of stalls and they are very informative, and they will tell you about latest happenings in the field of geotechnical earthquake engineering, and also provide you information about various societies and various other activities. Please, all of you, please do visit. And that exhibition hall responsibilities are taken care by our Dr. Parthasarathi. He is the vice chairman of this conference. He is here. Sir, would you like to add anything, Dr. Sarathi?
Thank you, Raviji. I think there are many stalls. Exhibitors have come to participate in this program. So all the participants are requested to visit each and every stall. So to know more about the products and services they are offering. There are some professional bodies like TFI, IGS, and ISET. So you can download some brochures and get more information of the upcoming programs. There are some companies who manufacture drilling rigs from US, from India, and there are some companies who manufacture testing equipments, and there are companies who sell softwares. Particularly, you can get to know about the latest software that is available for the application geotechnical and civil engineering. So kindly I request all the participants to visit the exhibition stall and encourage the exhibitors so that they also feel overwhelmed with your participations. So with more of technical feast, even that is also part of our conference. So kindly I request that please visit the exhibitors stalls. Thank you.
Thank you.
Thank you, Dr. Parthasarathi. And I also request all our participants to visit networking launch, where you can interact one-to-one with experts live using video chat and text chat, and also visit our e-resource corner, where you can get all the information, the presentations shared by our speakers, and also the manuscripts and keynote papers. Everything are available through e-resource corner. With this, we are closing this session, and the next session will be starting at 4 p.m. onwards in parallel halls. You are all requested to join us at parallel halls. Thank you, one and all.
Thank you.
Thank you.
Bye.
Thank you.
Bye.
Thank you.
God bless. Okay. Bye. Take care.
Okay.